Let's do this. Molar mass of carbon dioxide is 44.01 grams per mole. This means that 44.01 grams of CO2 are in every mole of CO2. How many moles of CO2 are in 2.37 grams? Now, just an aside here that applies to this, all right? It's important that you give capital letters where capital letters are supposed to be and lowercase letters where lowercase letters are supposed to be, okay? Element symbols always have a capital letter. If there's a second letter, the second letter must be lowercase. And that doesn't mean you can make a smaller capital letter, okay? Write lowercase letters where they apply, okay? And be careful. Make sure letter I's look like capital letter I's and not just might be mistaken for a lowercase letter L or a number 1. Okay, be careful about that. It's important that you're clear. So if you weren't going to write CO2 as in carbon dioxide, capital C, capital O for carbon and oxygen, don't put C and make this O look like it's a lowercase o, because a C with a lowercase o is cobalt and not carbon dioxide. Okay? Got that? Or carbon monoxide, C, capital Z, capital O, could be mistaken for cobalt if you write capital C and what looks like a lowercase o. So be careful about your uppercase and lowercase letters. It's really important in here, okay, that you're clear. All right, so you can solve this problem, work with a neighbor, a learning partner, and then I'll come back behind that and show you how to do the problem, okay? So this is the unrounded answer. That's the rounded answer. Everything's required, all the units and measurement, all the species, all the cancellation. I'm not sure where you got 2 significant digits. There are 1, 2, 3 significant digits here, 1, 2, 3, 4 significant digits here. And when you're doing multiplication and division, you look at the total number of digits and all the measured or calculated numbers and choose the number with the least digits. Yeah. So this is the one with the least number of digits of the measured and calculated numbers. This is a measured number, this is a calculated number. So this would have 3 significant digits. You want your final answer to have the same number of digits. That makes sense? Okay, so here's a new problem then. The density of nitrogen oxide, which is NO, both capital letters, is 1.34 grams per liter at standard temperature and pressure, and that's STP. What volume would 12.75 grams of nitrogen oxide have at STP? Now we went over, I think, yesterday, how this can be used to figure out an equality statement, okay? So you might want to go through that process before you try to solve this problem. Figure out your equality statement first. The important thing is that you know that 1.34 grams per liter of nitrogen oxide means there's 1.34 grams of nitrogen oxide in 1 liter of nitrogen oxide. And the reason you know that is you can rewrite this fraction like this. Okay, so grams per liter means grams per liter in this fashion. And so if we have a fraction like this, we know that conversion units of this type come from equality statements of this type, and so then I know I can just reverse it here or build it like this the way you've been taught to do it. Okay? And that's what I want you to understand, because otherwise you get confused, like some of you apparently are, okay, about how to get the right answer. Okay? I want you to know where all this comes from, and then you know how to use it. Okay? That makes sense? You're going to have a bit more tools in your toolbox because you know what it means, not just what a number is, and plug it in somewhere. Okay? There are times in this class where we'll do plug and chug math, but this is not what we're learning right now. We're learning how to build the math. Okay, so the fraction, grams over liters, is the same thing as saying grams per liter. And if I use the words grams per liter, it means grams divided by liters, okay? Or grams per mole if we're talking about molar mass, okay? Grams per mole means grams over moles, okay? If I'm writing grams per mole, I'd be writing 44.01 grams over a mole, okay? But that kind of means the same thing here, all right? All right, so here's a practice problem for you to do, and this will tie in both dimensional analysis and writing equality statements and the significant digits, the scientific notation that you guys were asking about. So we'll solve this problem, and I'll let you solve it and see how you do, and then after that I'll come back and we'll see what holes we need to fill in what you understand. So solve this problem now. Okay, so let's look at how to set up this problem then. We want to know what part of this problem, what measurement or calculated number of the problem sort of stands alone by itself. That's our starting amount. So reading the problem, the part of the problem that kind of stands alone is this 451.3 moles of propane. So that's going to go on top of a 1. 451.3 moles. And we said propane is this formula here, so I'm going to use C3H8. You could use the word if you prefer, okay? And we're going to put that over 1. And then we're going to look at the problem and see, well, what two things seem to be equal to each other? Because we're doing a conversion. We're going from moles to heat, so we're converting. So what two things tell us how moles and heat are related here? Well, that's 2,220 kilojoules of heat from 1 mole. Now that's not a true equality statement, but we'll find out about that later on. That's about unit 5 before we get there, okay? So right now we can treat it as if it is a true equality statement, okay? But just a warning that it's really not. So let's see, we got 2,220 kilojoules of heat is equal to 1 mole of propane. Okay. Well, if those two things are equal, then I have what I need to build a conversion unit. I just need to find out if the starting units and species match some side, one side or the other, of this equality statement. And indeed, this right side matches the same units and species. So that part of the equality statement needs to go on the top. 1 mole of propane goes on the bottom here. And the other side of the equality statement needs to go on the top. Now, if I've set this up right, then the units and species that I can cancel will leave me with only the thing I'm looking for. And let's see what happens. So moles can cancel because we got moles on the top and bottom. Propane can cancel because we got propane on the top and bottom. And I'm left with kilojoules of heat, and the question is how much heat is produced. So I know I'll probably set it up right. All I got to do is do the math now, okay? All right, and I get 100,1886 kilojoules of heat. Okay? Make sense? Now we have to round it off to the correct number of significant digits. And to get the correct number of significant digits, then I need to look at all the measured and calculated numbers, because this is multiplication and division. And the rule in multiplication and division is you're going to look at all the measured and calculated numbers and only the measured and calculated numbers, and find which one of those measured or calculated numbers has the least digits, and round your final answer to that same number of digits. So it's least digits here. Well, in this case, this number has 1, 2, 3, 4 significant digits. And the rule for significant zeros is that trailing zeros, or at least the informal rule, says that trailing zeros, when there's no decimal place, are not significant. So this only has 3 significant digits. The formal rules state that zeros have to be between 2 significant digits to be significant, or have to follow both a decimal place and a non-zero digit. This 0 follows a non-zero digit, but it doesn't follow a decimal place. So using either set of rules, either way of looking at it, this 0 is not significant. So we need 1, 2, 3 significant digits. So we count 1, 2, 3. Those are our significant digits. Underline everything else and round it off. Okay? Now, we're getting rid of a number in the ones place. Okay? We're also getting rid of a digit in the tens place, and a digit in the hundredths place, and a digit in the thousands place. But the only thing that really matters here for the rule about writing in scientific notation is we're getting rid of a digit in the ones place. Okay? If we're writing a number, getting rid of a digit in the ones place, we're rounding off a digit in the ones place, then we must write in scientific notation. And in scientific notation, the decimal place must go immediately to the right of the first non-zero digit. First meaning reading from left to right because we're reading in English. So starting from here, this is our first non-zero digit. The decimal place needs to go right here. So we're going to move our decimal place 1, 2, 3, 4, 5, 6 places to the left. Okay? And so we're going to write 1.00 times 10 to the 6th power. Because I moved it 6 places, it's 10 to the 6th power. And that's kilojoules of heat. Small letter J, K, capital letter J, heat. Okay? And there's our answer. So I've combined a lot of things in this one problem. Dimensional analysis, rounding properly, keeping up with units and species, and scientific notation. Okay? Yep.
Dimensional analysis is like setting up an equation?
Yeah, dimensional analysis is where you set up a conversion equation. It can be other kinds too. We won't get to that to Unit 5. Equations in this form, where the units and species can cancel out, leaving with what you want. Okay? So you're analyzing the dimensions. Dimensions meaning the measurements, the area of measurement. Okay? So moles measure the amount of stuff. It's the SI unit of the measurement of the amount of substance. Okay? Our kilojoules is a measure of energy. So energy there is the dimension. If we were using grams, that'd be the dimension of mass. If we were using milliliters or liters, that'd be a dimension of volume, or cubic decimeters, I guess, okay? Because that's the SI unit, I think, of volume. We use liters in here, same thing as cubic decimeters, but I think if you look at the SI system, you'll find that cubic decimeters is actually considered to be the SI unit of volume, okay? All right, got that? Now, there's a dimension of temperature. So when we say dimensional analysis, it's really talking about the units of measurement more than it is talking about the species. But we use the same process for canceling out species. Okay? It works out better in chemistry. In chemistry, we can use that process to cancel out species as well. In physics, you wouldn't have species. Very often, you wouldn't have species anyway. All right, so the question you're asking about is number 43 here. And obviously, I got a strange-looking number there somewhere. Let's see if we can fix that right quick. How about this? All right, so the density of magnesium from your test references is used to determine the mass of a sample of magnesium that takes up a volume of 5 milliliters. And so 5 milliliters must be our starting amount. Okay, so we're going to put 5 milliliters on the top. Magnesium is capital M, little g. Okay, and if you look on your test references, the ones that you'll use on the test in an honors class would be like this. And you kind of got to know that that's magnesium. Now, I'll try to help you out on the first test, but eventually you guys got to know what most of these symbols mean, because you notice the names are not on here. Okay? And that's because this is a prerequisite class for AP, and in AP, this is the kind of periodic table you're going to use without the names on there. So you got to kind of know what they are. The main thing that students get confused about magnesium is here, and manganese is here. That's what they tend to confuse the two. You just need to know the difference, okay? You don't very often need to know the really large elements down at the bottom, but sometimes it comes up. So you need to start familiarizing yourself with how the symbols relate to the names. You'll have the symbols, you just won't have the names, okay? But now the first test, I'll try to help you out. But over time in this class, you're going to have to know the names. All right. So our starting amount is 5 milliliters of magnesium. And using that, what the density is, and even though that's on the practice test that way, I'll have to give it to you because you don't have this set of references actually in your set of test references. But here's the density, 1.74 grams per cubic centimeter. So the density of magnesium is 1.74 grams per cubic centimeter. Okay? And I told you guys already that you need to know that when you see a density written like this, you need to know what it means. You need to know what is what information we can get out of that. And so out of this, we can get this equality statement. We say 1.74 grams of magnesium equals 1 cubic centimeter of magnesium. Okay? So what else you need to know is that a milliliter is equal to a cubic centimeter. Okay? And if you're going to go into medicine, by the way, cubic centimeters are often written like that. So if you've ever heard cc's, so many cc's of something, that means cubic centimeter, which is the same thing as a milliliter. Okay? Just got to know it. All right? So let's see, you need to know something about, I say you know 1, 2, 3, 4 prefixes in the metric system. You've got to know kilo, centi, milli, and nano. Okay? Kilo, centi, milli, and nano. If you know those 4, you're set. All right? But that happens to be the same as that, which you kind of need to know, and that's the same as this. You don't really need to know this because we're not dealing with medicine here, okay? You need to know these two things. So, if we have this, then because this is equal to 1 cubic centimeter, it's also equal to 1 milliliter of magnesium. Okay? So now I've got the equality statement I need. I can put this on the top because I'm trying to find the mass. Okay? This is what's the mass, and grams measures mass. Okay? Milliliters measures volume. All right? So grams is 1.7. I'm sorry, I need to put 1 milliliter on the bottom because I got to match the units and species, top and bottom. 1 milliliter of magnesium goes on the bottom. And then the other side of the equality statement, the part that I need is this over here, 1.74 grams of magnesium. And we do the math. And so milliliters are going to cancel. Magnesium is going to cancel. We're left with grams of magnesium, which is what the question is asking for. Get out your trusty calculator. And 5.00 times 1.74, and we get 8.7 on the calculator. How many significant digits do I need in my final answer? 3. I'm looking at the measured numbers and calculated numbers. And of the measured and calculated numbers in a multiplication division problem, we're going to choose the measured or calculated number with the least digits. Both of these two have 3 significant digits. And so we want our final answer to have 3 significant digits. But we don't have 3 significant digits yet. What do we need to do? Put a 0 there. Now we have 3 significant digits. Okay, and that's grams of magnesium. And there really isn't any reason to round off here. Okay? Does that make sense to everybody? So you have to round off when you have to round off. But you don't round off if you don't need to. Any questions? I mean, if you drew an arrow and put the same number, I wouldn't count it wrong, but there's no reason to do that.